we get here?
Yeah, how did we get here?
Oh, Dan, look at those juicy local variables.
Kyle, you fucking serious?
It all started with a comment suggesting that Ford would be easier if one used local variables. Well, that might be true, but you'd lose a lot of hidden benefits in the process. In my humble opinion, that is. Which resulted in my Ford is dead video, because that's the consequence when you insist on local variables. In my humble opinion, that is. If you're wondering why it took me a full month to get that one online, I needed at least half that time to do the research, whether by lifting the proper documents or by fetching the music and doing the actual programming. So, in the end, what do you got? Just a lot of disjoint paperwork instead of a story you wanted to tell. And after constructing the narrative, a lot of material is left on the cutting floor. More than enough to tell another story. And that's how we got here. I'm not saying I'm covering everything that has been published on local variables, but a lot. That which was easily accessible on the internet. At least enough for a compelling narrative, I think. So, let's get started.
Flashback.
As far as I know, the very first article dedicated to local variables was published in 1982, even before the release of the disastrous Ford 83 standard. It is typical of those first implementations, and requires that the stack can be accessed directly by fetch and store, something that 40H doesn't allow. It also requires you can query the stack pointer, so you can calculate the addresses of the individual stack elements. Let's say you want 3 local variables, then you work out the address of the third of stack, name it, and repeat the procedure for second of stack and top of stack. No matter whether you add or remove any stack elements, the addresses remain the same, although they may have been invalidated in the meanwhile. When exiting, you might want to create a suitable stack diagram, for instance by discarding superfluous elements from either the shadow stack pointer to the actual stack pointer or vice versa. That's basically the method used by Mark Burkle. I made a quick port to Ansford, and it still works perfectly. You can even nest procedures with local variables. It also features a value-like implementation, avant la lettre. I think it's cute. A variant of this idea was published by Leonard Morgenstern a few years later. We'd have to wait until 1984 to get another locals design, this time from Ronald Green. It's based on fiddling around with vocabularies, a concept I know very little about. Since the article does not include an example, I have absolutely no idea how it behaves in the real world. Now let's jump to 1987 and Peter Ross's design. He's part of the school, I want the syntax, now I'm getting it no matter what. I intensely dislike this school, because when you disrespect a language, you're bound to create needlessly complex designs. And for that reason, I didn't even try to figure this algorithm out. It's there, I mentioned it, period. The next year we have a surprisingly familiar design from Henning Janssen. As a matter of fact, it's almost identical to the brilliant one-liner by Fred Berenger and Albert van der Horst, which we examined in a previous episode. But it's criticized by Michael Barr, who cleans up the syntax and creates an assembly version which, he claims, is much faster, but most certainly less portable. However, that same Michael completely destroys the Peter Ross design in the same letter, mainly because, despite its elaborate design, it can't handle a simple recursion. In that same issue we find the design by John P. Dougherty. It basically works by tinkering with the dictionary in a way that I doubt is portable, and is, at least in part, based on the design of Ronald Green. At least he adds an example. You have to define the variables outside the procedure and clean them up manually. Fred does it better. In 1989, Henning Janssen hits back at Michael Barr with a local definition that eliminates the function call overhead by merely inlining the code. Folks, it will never get as fast as C. Often good is good enough. There are more qualities to code than just speed. And if you want speed, why use locals that have to be constructed and destroyed? In that same year, almost an entire issue of 4 dimensions was dedicated to the subject. As usual, local variables are presented as a convenience that improves readability. I can understand that. Forters are first and foremost pragmatists. They first have to bump into the consequences of those fundamental errors before they change course. And at that moment there was not a great deal of experience with this concept. But I digress. The first method, designed by Jyrki Elinokari, I definitely murdered that name, bears some resemblance to the Mark Perkel implementation. Only here stack frames reside on the return stack. Also, his implementation distinguishes arguments and local stack frames. Also note that deallocating stack frames is achieved by an equivalent of the semicolon-colon definition of Albers van der Horst. Very clever. Now, how do stack frames work? Either in its own space, the data stack or the return stack. It begins with a pointer, pointing to the current stack frame. Then we have a pointer that points to the previous stack frame. Simple. Yeah, that first stack frame contains either null or another special value, indicating this is the end of the line, folks. Now, let's assume we are calling a word. First thing we do, create a new stack frame with a pointer pointing to the previous stack frame. When it's time to allocate the local variables, we move that pointer down. If our stack grows down, of course. And now we've got created space for, in this case, 3 wonderful local variables. If we encounter exit, we set the stack pointer to point to the previous stack frame, using the pointer of the now decommissioned stack frame, which effectively removes the stack frame. Now, the quirky thing of this implementation is that we can address the local variables by one of 3 methods. By feeding it an offset to the current stack frame, by naming the local variables, or by using default names not unlike Mark Perkel. A striking detail is, those are created using method through. And we continue with another one, this time by José Betancourt. He is also part of the school I want the syntax and now I'm getting it. So I'm not diving into that one. What I found most intriguing was his statement, a simple task such as subtract B from A and subtract C from A will require many stack operations. Because, is that true? No, it's not. Of course it's not. That is, if you actually know Fort. Then it's easy. Let's first examine the local solution. Let's disregard all initialization and focus on the payload. At least we need to fetch 4 variables and do true subtractions. Let's add that together and say about 6 operations. Now, let's do it the classical way. Let's get B and C out of the way. Then duplicate A and retrieve B, subtract them, and we got A minus B. Bring A's duplicate to the front, retrieve C, subtract them, done. 8 words in total, that's it. We can even save one more word by just moving C to the return stack. That's 7. What do you mean, many stack operations? It's 1 more than your local solution. And I've been extremely kind. I didn't count any fetches. I didn't count any constructions or deconstructions. But it's simply not true. If you make that claim, you're just showing you don't have any proficiency in Fort. But that's all we got time for today. Next time we see how Fort finally embraced local variables, and consequently died in the process. And ending on that positive note, I'm Hans Bezemer, and this was Back and Fort.